Alright, we're in the black again with video number 2. So we left off with how do you make big sparks with rubbing stuff together with one liking electrons more than another. Okay, well now we're going to talk about charge by conduction. Okay, so when a charged conductor makes contact with a neutral conductor, there's a transfer of charge. Alright, so here's a good example. There's your wand. It's already been charged with something that doesn't like electrons as much. And as you bring that nearby and you touch that little, could be a pith ball or whatever, it can conduct or transfer some of those extra electrons. Because remember, all these electrons repel each other. So if they have something neutral, they might jump off from your wand or conduct off onto the wand, and maybe you'll lose half of them or some of them or whatever. Then, as soon as some of them conduct onto there, now this repels the wand because they're both still negative. Okay, that's charged by conduction. You do the same thing positively, but you need a different source to rub your wand there. So electrons are transferred from the rod to the ball, and now they're both negative. So if this had 10 extra electrons, 5 might be there, 5 might be there, 4 might be there, and 6 might be there, depending on which one likes electrons the most. Or really, rather than 5 and 6, we're talking about bazillions. Okay, so this is rubbed with something that likes electrons more, stripped them off. It has a lack of electrons. So now when you touch this ball over here, what happens? Electrons tend to jump off of the ball onto the rod. And as electrons jump off of the ball onto the rod, now the ball has less electrons, or it's positively charged because there's less electrons. And this is less positively charged because the electrons jumped onto there. So if 10 of these jumped onto the rod, this has 10 less electrons. This has 10 more electrons than it had before that. It's a law of conservation of charge. But in either case, it's charged by conduction. You touch something and you had a transfer of charge. And normally it's the electrons doing the moving. Sure, you could have positrons, but there are not that many positrons. Normally it's electrons. Some other day we'll talk about the holes that are moving, which is a whole different story altogether. Let's just talk about electrons for now. So the transfer, okay, we said that already. Alrighty. So remember, only electrons are free to move in the solids, okay? For the most part. Not completely true, but that's what we'll stick with for now. Good enough for our AP2. Alrighty. Notice that the original charge object loses some charge. Yeah, we talked about conservation of energy. There's nothing there in the animation. Alrighty, charge by induction. So conduction, charge is moved from one object to another. Induction, no, not really necessarily moving from one object to another, just within an object. So here we have a charged rod over here. This used to be, well, it is neutral, still is. There's as many negatives as there are positives. But what happens, since this is a negative, you got it near charged by induction, electrons are repelled to the other side. So if you repel electrons from this side to that side, you have a lack of electrons here, which makes it positive, and negative here. That's charged by induction. You didn't actually transfer them out of the body or from the wand to there. As soon as you take the wand away, they go right back to where it's still neutral. Overall, it's still neutral, but we have a positive side, negative side. We've polarized it, okay? At least for the moment, okay? So charge rod brought near there, the influence charge, you can read. Hey, we're going to do something else special, guys. We're going to connect this to the ground. That means to the ground, the earth is a ground. The earth was what charge? No charge. The earth doesn't have a charge, folks. It's very, very big, and there's no net charge. That's why we call that the ground. It's not positive, it's not negative, it's just the ground. So if we connect a wire to that, what happens is, since this is neutral to the ground, those extra electrons, some of them go zipping into the ground. Not all of them, but a bunch of them do. So now the sphere has a net positive charge. However, if you pull that wand away, guess what happens? Being positive, electrons tracked right back on and still neutral overall. It's charged by induction. Okay? And more words down there. So what would happen is when we did this, but we left the rod there, and we took the ground off suddenly. Because in reality, we conducted electrons into the ground, right? So that's not charged by induction anymore. So it's charged by conduction after we pull this wire away, because remember, electrons were conducted out of the thing. And that's here. So now we took the wire away and it's an overall positive charge. But even though they're calling it an induction, technically we conducted some of them off into the earth. Okay? So that part was actually charged by conduction. And now we have a net, take this rod away, we still have a net leftover positively charged object. And that's special. All right. So the object charged by induction has the opposite sign of the influencing body. There we go. All right. Original charge object does not lose charge. It's none transferred from there to there. Okay. There's no animation there. There's the hat trick. That's not going to happen. All right. Electric forces, electric fields. Okay. So we'll get to the fields in a little bit. This is going to focus just on the force stuff. That's the math that you're not going to like. It's not that fun, but you get over it. Coulomb, he loves math, by the way. Probably. He looks like he loves math. Looks like a sailor. Faraday, you've heard a lot about this guy probably. He's pretty famous for doing a lot of electromagnetism stuff back in the day. He's after this dude over here by quite a bit. Much more famous than this Coulomb person. Well, this Coulomb person did some experiments. It kind of started the whole thing going off of electric charges and what kind of forces are on things. So now we're going to talk about a new fundamental physics quantity. Traction repulsion. Well, we've talked about that. The same repels, opposite attract. Okay. It's an action-reaction thing. A can't push harder than B pushes on the A. A can't attract B harder than B attracts the A. So electrostatic charge is a fundamental quantity like length, mass, and time. There is a certain amount. We're getting to what that charge is for that Q. Q stands for the charge, and it's going to be measured in coulombs. After that Coulomb guy looked like a sailor. And he could be a sailor, I don't know. So, didn't know this in Coulomb's time, but later on, we found out near the turn of the century, the 1900s time, that the smallest charge you could get is this. 1.6 times 10 to the negative 19th coulombs. After we already just tried to describe what a coulomb is. This is the smallest they could get. They couldn't get any smaller than this. That means it's fundamental. That's as small as it can be. So a positron would be that much charge. A proton would be 1.6 times 10 to the negative 19th. An electron would be negative 1.6 times 10 to the negative 19th. But that's the smallest charge you can have. It's fundamental. Oh, there's your proton right there. We just talked about it. What if its ears are burning? Common electrostatic charges are small. So yeah, 1 coulomb is a frick load of charge, guys. We're not going to, in lab, if you were actually in lab, you wouldn't be dealing with a coulomb of charge on something. That's a tremendous amount of charge. Millicoulombs is still a lot of charge, 10 to the negative third. Microcoulombs, that's more on the normal side of things. Even nanocoulombs are normal charges that we're going to be dealing with between objects. Okay? So nano is 10 to the negative 9th, micro negative 6, milli negative 3. We're going to be using a bunch of those. M is for milli. Mu, not an M, is for micro, and the N's for nano. All right, now let's do more of that electric force stuff. All righty. Coulomb and his torsion balance. So here's what he did. He put on a thin wire, he charged some balls up, and he noticed there's a force of attraction or repulsion depending on how we charge those balls. And by knowing the tensile strength of this, or how much force it takes to twist that string, through some other experiments, you can actually measure forces between these charges. But how did he know actually how much charge was on these things? That's actually kind of a trick, in his day anyway, not in our day. So is able to measure the force between small charges. You already did that in your lab situation already on Tuesday. A little bit different method, just by a ball suspended from a ceiling charging another ball, knowing what the charge is on the balls though. So it depends on how big the charges are. The more charge you have, the greater the force. Okay, so you already found that part. So it depends inversely on the distance between the two, or it's the inverse square law. So you learned about the inverse square law with gravity. Well, it's any kind of a field is an inverse square law because the field stretches out this way. You get twice as far away. You have 1/2 the field this way, but 1/2 the field this way. 1/2 times 1/2 is a fourth, or it's a fourth the strength. Or if you get 3 times further away, the field stretches out 3 times this way. It stretches out 3 times this way. So it's a third by a third, and a third times a third is a ninth, or 1/9 the strength. That's the inverse square law. So there it is, guys. The K is a constant. Q is one charge. Q is the other charge. So there'd be a Q1. There'd be a Q2. The R is the distance between these two, center to the center. The center to the center of the distance, and the K is a constant. That's the electric force, E sub E for electric force, between two charged objects. Okay, that's electrostatic force. There's your distance, there's your charges, and there's your constant. Say, what is that constant? 9 times 10 to the ninth. It is. It's 9 times 10 to the ninth Newton meter squared per Coulomb squared. That's a constant, means we don't change it. Now that's what it is if you're in a vacuum or pretty much air. They're pretty similar, at least the 2 sig figs. Okay. You put other stuff in between, that could be a different value for whatever's in between these two things. But as long as it's just talking about air, vacuum, the 2 sig figs, it's at 9.0 to the ninth, not negative or anything, positive ninth Newton meter squared per Coulomb squared. Seems like a big number, but remember, we're not going to be dealing with very many coulombs. We're talking about very, very small amounts of it. So we're not talking about tremendous forces. Oh, so here's the story. A negative times a positive is a negative force. In physics, negative forces are attractive. A positive times a negative, well, that's still a negative force. That's attractive. A positive times a positive is a positive. That's repulsive in physics. A negative times a negative is still a positive. That's repulsive in physics. So negative forces in physics are attractive. Positive forces are repulsive. Okay? Alrighty. Time for a couple more slides here and some math. Alright, find the force between these two charges, guys. There it is. Micro, 10 to the negative 6. 4 centimeters, that's 2 places. Centimeters is 2 places to go to meters. You got to be in standard units because of that K thing. So yeah, they do attract each other because they're opposites. So let's do the math. 9 times 10 to the ninth, 5 times 10 to the negative 6 because it's micro, negative 8 times 10 to the negative 6 because it's micro, smaller than 1, and we change 4 centimeters 2 spots over to meters. Don't forget to square the bottom, and bam, whoo, wow, that's a good size force, guys. Because that's a lot of friggin' charge, even for the micro, and they're close. Not as a lot, they're only 4 centimeters apart. So that's a pretty good sized charge between those two things, attractive charge of 225. Okay? So yeah, the negative doesn't mean left or right, guys, it means attractive. So find the net force on the left charge. That was the force between the two. But what happens when we set them up like this? Well, here's the good news. We already did this one, guys. Okay? So we already did the 4 centimeter. We need the force on this side over here. So find the net force on the left. So we already know the force is attractive this way on this left one of negative 225. Now we have to do this whole thing all over again for these two. Oops, I'm sorry. Not for those two, for these two. Because we already did the orange one in that one. Or not orange. Orange is the new yellow. Or the other way around. Anyway, the repulsive force here. Bam, let's do that real quick before we run out of time on this one. Alrighty, so the 9 times the 5 to the 6, 5 to the 6. Remember, it's 2.5 centimeters. 2 places over 0.025, 360. So you got a 360 repulsive, purple, a negative 225. Negative means it's attractive. It's going the other direction there. And you can see the 360 to the left is bigger than the 225. Add these two things together, and what do you get? You get 135 to the left. Boom. Okay, that's the end of video 1. You have to memorize those numbers for, that's video 2 actually. For video 3, we're going to come back and look at that again before we do video 3. Alrighty? So, because 3, we're going to go not one-dimensional, but 2-dimensional. Are you excited for two dimensions? It's one better than one.